Hi everyone, thank you for tuning into this presentation. My name is Gabriella Joyce and I will be presenting my research, Robotic Connections for Clt Panels. With the climate in a state of emergency, the construction industry needs to take responsibility and move towards a more sustainable built environment. Construction is one of the biggest contributors to landfill waste, and the use of concrete and steel make up 9 to 12% of global greenhouse gas emissions. This research focuses on the use of timber as a primary construction material, specifically cross-laminated timber or CLT. CLT has numerous benefits, including high shear and axial load strength, along with good thermal, acoustic and fire performance. However, the development of an optimized connection system remains a key concern. Thanks to developments in digital and robotic fabrication, there are now more opportunities than ever to explore connections. With the influence of traditional Japanese joinery and existing CLT connection systems, this research uses computer-aided design and a 6-axis robotic arm to explore the question: how can advanced digital fabrication be used to design connections for CLT panels with minimal waste? Using a research through design approach with a focus on iterative prototyping and evaluation, this research started with a literature review that identified key issues within the CLT construction process, before conducting an evaluation of existing connection systems to create a base for design. From here, the design and prototyping phase was used to test both the design and fabrication techniques to develop and inform future designs. These designs were further refined following an investigation into factory fabrication and real-world application. In order to evaluate the designs, an assessment criteria was developed based on key issues identified in the existing systems. These are the aesthetics, the number of pieces, the wastage potential, the ease of building, the ease of fabrication, and the thermal bridge potential. In order to address both the thermal bridge potential and the aesthetics of the connection, the first step was to completely remove metal fasteners. This decision has the potential to reduce the number of pieces required and reduce wastage. Based on this, the designs are influenced by traditional wood-on-wood Japanese joints. These traditional joints are designed to be used as beam and column connections, not as panel connections. So the first design challenge consisted of finding a way in which these joints could be adapted for panel construction, whilst maintaining the proportions and shapes that create such successful joints. Having started the design process with the repetition of these Japanese joints, it became clear that this was far too complex. The existing connection systems are achieved by adding external pieces, such as a screw, to the construction. Though using metal pieces such as this is not the goal of this research, the idea was taken forward in the form of a timber key. The traditional Japanese joint, the dovetail, was adapted to form a key and tested against the assessment criteria. The key showed to be far more successful than the repeated dovetail in all areas, so this idea is what will be developed further. Using traditional Japanese joinery systems as a base, a series of designs were created with varying degrees of complexities and different number of pieces. From this, 4 designs will be taken forward to be prototypes using the robotic arm. The prototyping of these designs was undertaken using an ARB 6-axis robotic arm with a spindle attachment. Given the nature of this research and the large scale of the material, the 20mm milling bit was used, as it allows a deeper cut and a simpler toolpath to create the key shape. In order to control the robot, a code was developed in Grasshopper for Rhino using a plugin, HAL Robotics. The nature of this code means that the user has absolute control over every part of the process, from the design to the way the robot moves and the speed in which it does so. The robotic arm executes tasks by following a defined toolpath created here. This toolpath is then converted into rapid code along with the tool and speed instructions to direct the robot. In order for the robot to understand the instruction, curves created in the design phase are translated into targets with a directional plane that define where the robot moves. This plane is crucial as it determines the angle in which the robot executes the movements. This toolpath creation process is where tolerances are crucial, both for correcting forms to account for the bit radius and for the spacing of the targets. If the tolerances are out, so the joint will be. Prototyping. The design of a connection system such as this means very little if it can't be applied to industry. Though there are differences in every factory, the base procedure of creating a Clt panel is the same. Timber lamellas are sawn down and finger jointed before being sorted into long and cross laminations. They are then stacked at 90 degrees to each other before being bonded and glued. Once pressed, the panels are cut to size in a gantry-style 5-axis CNC machine. This process has been designed to create as little waste as possible. However, there are often panel offcuts that cannot be recycled as they are treated in the factory. As the connections designed in this research use timber and are intended to be used for Clt panels, the fact that the waste timber is treated is irrelevant for this project, and therefore can be used to create the keys. This allows for the manufacture of the keys to take place in the factory using existing tools and creating a much smoother process and reducing waste. As the CNC machines used in Clt factories are gantry style and able to process 16 meter by 3.6 meter panels, it would be inefficient to cut one key at a time as I was doing in my prototyping phase. This is where the idea of tessellation came in. Tessellation allows the keys to be cut out of waste panels in a repetitive pattern, which reduces the waste and creates a faster cutting time. This chosen design uses the most successful qualities from the previous prototypes: simplicity and a wedge-shaped center, combined with the proportions of a traditional dovetail. This design was then rationalized and developed to create a simpler cutting path and the ability to parametrically alter the design based on project-specific requirements. This means that the number of keys and the size of the keys can change with each project, with very minimal interference or changes to the design. The research undertaken offers many possibilities for future research into improving this connection system and applying it on a large scale. Structural testing could be undertaken to determine the strength of the joint under more rigorous circumstances, including earthquake simulation. The system could also be tested in a factory situation. If the speculated factory fabrication technique using waste and a CNC router could be tested, it may become clearer as to whether or not this is a viable solution for waste minimization. It would also be interesting to compare the cost of a situation such as this compared to existing Clt construction systems. It became clear through this research that there is no one solution to this question, and that there are a number of factors to consider when designing. Using robotic prototyping and simulation, it was determined that maintaining simple forms and including wedge shapes would create the most successful system. Though conclusive statements cannot be made in regards to the success of this system on a full building scale, the link between digital fabrication and connected technology has been made and has highlighted the potential for further exploration. This research has shown that timber connections for Clt panels can reduce construction wastage through the use of digital design and fabrication. Thank you. The prototyping process highlighted that the key needs to be a perfect fit. Too tight and the joint doesn't come together. Too loose and the joint is weak. Along with this, the prototype showed that the simplicity of the key and the use of wedge shapes creates a stronger joint. Simplicity comes in both design and fabrication. The simpler the design, the faster the cutting time and the cleaner the cut, meaning the right fit is more achievable and assembly is far easier. The use of a wedge shape to complete the connection means fabrication is not as simple, but it creates a much stronger joint that is less reliant on it being the perfect fit, as the wedge creates friction that pulls the pieces together. The process also highlighted the importance of working with the machinery. The milling bit is rounded and has a much better time creating rounded shapes, therefore the fits are better. This does, however, reinforce the importance of tolerances. The robot will always find the easiest path, and that is usually a straight line. So, when creating a curve, there needs to be much more targets in order for the robot to create a clean curve. These targets then need to be replicated exactly for each piece of the joint. Though these are all robot-specific issues, they provided valuable insights into machine processing and the role of tolerances and tool selection in manufacturing. This learning is key when considering how a system such as this could be applied on a larger scale and in the wider industry.